So today I will talk about what I call collectionless AI and nation-inspired learning. But the focus, as you will see, is on this keyword, collectionless AI. I will do my best for communicating what is happening, at least with a few colleagues worldwide. And essentially, the motivations are mostly from nature-inspired learning, but you will see that I want to give you a picture that it's broader, and most importantly, is a picture that in no way I can claim, that it's my own picture, right? There are a number of people who have been contributed remarkably to the establishing of this terminology also. But you see, one of the point that I think is critical is I really want to see whether we are, condemned to the sole intelligence that emerged from brute force. That's the question, right? And I think that this is a nice question for people like us. We are at the university and not in top-level companies. And I'm confident, everybody here in this room pose himself this question, maybe in different ways. As I told you, this is not something which come at the end. When you propose something like this, there is a process. And there was quite a long path, at least from my for the digestion of this idea. I think I had the privilege of being inspired by a number of people. I'm sure the role that even without knowing, but people like Tommaso Poggio, had in my way of thinking concerning nature-based nature inspiration in learning. And the interaction I had, for example, with people like Naftali Tishby, Joshua Benjo, and recently Jay McClelland, but especially very recently with Alexei Efron in an international school that we organize, I think has been very important, together with the role of this collectionless AI team, where there are a number of people. Not only in my university. And also this school, we organized recently an international school under, the keyword collectionless AI. And I think, it was interesting to see how different people, come with ideas that are not very far away, right? So this is what I will tell you about today. I will tell you what is collectionless AI. So these are tend to go beyond brute force. And we'll just briefly mention how, machine learning and artificial intelligence could dramatically change if you take a different approach to the discipline, which, put the emphasis on natural interactions. But this is, maybe the part I like most. This is what I really love, But today I will not go into details concerning the second part. My task today is also to tell you briefly of what we call Universe. It's a technology that, it is currently under development. Which has evolved my initial idea on this NARNIAN project, and so I will tell you briefly how we could push also from a technological point of view these ideas. And so, if you want to have a look in a very compact way of this idea, there is a brief paper, which is appearing on the Communication at the ACM. People in computer science probably know that it's the classical journal where you see brief contribution, opinion papers, right? So that's an opinion paper, simply an opinion paper which delivers the basic idea of collectionless AI, right? So you see the title, right? Reinventing AI. Is it the time for a new paradigm, right? And of course, it's for all of you. In no way, I pretend to have the solution. There are so many different ways of thinking. But so let's, tell you what is collectionless AI. I really need to focus a little bit on what is artificial intelligence in terms of evolution, right? I have the pleasure to see young people, right? Young people, of course, may not be fully synchronized, with all the steps of the evolution of the discipline. You see some remarkable, stages of the discipline, and well, there is quite a, people typically agree about the explosion of machine learning decades ago, which has completely changed, the face of the discipline, right? And we are seeing the connectionist wave during the 80s of the past century, and then deep learning, and then large language models and generative AI, right? But I think it's important to mention something which is not typically, let's say, considered. And I think, if you draw a picture like this, where you try to understand the evolution of artificial intelligence, it's important to realize that something happened in the last decades, and particularly the explosion, the idea of the web, right? The 6th of August 1991, Tim Berners-Lee, conceived the protocol of the web, right? And then, there was an explosion in technology, search engine technology, right, for distributing the information. Years later, together with two colleagues, we published a book. The title, as you can see, is Web Dragons, right? And the book was simply to notice that there was something a bit strange in the evolution of technology, right, with search engine, right? It was a bit strange because the original dream of Tim Berners-Lee was that of producing a sort of distributed collection of information, but at the end of the day, there were a few companies seated on the treasure of information which were handling everything, right? And so it was a sort of quite a normal association in the Western culture is the evil, right? But at the same time, there is a paradox because, the services of these companies are wonderful, are useful, right? Are useful for science, are useful for medicine, right? And so you are trapped in a sort of, intriguing, let's say, paradox, right? Which seems to be difficult to break, right? And then, a few years later, the artificial intelligence exploded, the maturity of deep learning, and then, other innovation on large language models, as you are seeing, are produce a dragon. You see, the dragon is the symbol from the Western and the Eastern culture of these two opposite views, right? From one side, wonderful opportunity for all the world, and the reverse of the side is that, you have somebody who is controlling everything, right? But now the situation is a bit more serious, I think, right? Because, it was quite obvious that the best way of handling from a technological point of view the search of information was to have search engines, right? With a sort of database which is a unique collection, right? A unique database. As you know, there is this crawling of information, then you put all the information in the database, and then you redistribute the information on the web. But now it's different. You have yet another dragon, but this time, as you know, there is an intelligent process behind, right? Which relies on big collections, right? Oh, great. So it's not just a matter of, the services that we have seen so far. And it's so nice and terrible at the same time to hear the typical keywords that circulate in Europe, especially, the officer of the European community, which typically use this terminology: privacy issues, transparency, trustworthy AI. What are they meaning? Nowadays, all, even research centers are in a situation which is depicted here, right? We are, the small animals trying to suck as much milk as possible. Somebody else is doing science at a higher level. So this is interesting, right? Because it looks like we at the university, we are just a bit down, right? A step behind scientists in those companies, right? So I don't see privacy issue here. Well, all the information are collected, right? And you collect everything, you put in the database of a few companies. And we are in Europe, we are noticing that the technology is mostly in China and in the States. And of course, it's refreshing to see that in Europe we are trying to track this technology, right? And this way of thinking, especially in a few countries. I've seen the role in France with a few companies that in France, very good. But is that the only possibility? Are we still condemned to follow this way of thinking? Okay, so that's the topic of today, seminar. Are we condemned to the sole intelligence that emerges from brute force? Well, if you have a look at the, computer science, you think of the history of computer science, you start from the slide rule, okay, then you go to mainframe, IBM mainframe, then in the 70s, we had the explosion of personal computing, and then with Google, we had the explosion of cloud computing, right? So why should it be the case that there is a sort of loop again, right? And you have again, the focus on small devices, right? Teeny devices, right? And intelligence on teeny devices instead of having these devices just as clients, right? They are still powerful computers. And I'm not talking simply of, a smartphone. There are so many computers worldwide, right? At an industrial level, right? Or not necessarily at the industrial level, which could become intelligent, right? So now, still looking at the discipline of AI, for all of you who took a course of artificial intelligence, the reference book is the one by, at least one of the reference books, I think the most popular. It's a seminal book by Norvig Russell. So I took the following exercise. I had a look at the topics, right? And I tried to cluster the topic. It's very easy, right? Because one possibility of clustering the topics is the one you see in this picture. So you see problem solving, and then you see knowledge reasoning, planning, uncertain, and reasoning. Those are topics mostly based on, semantics, algorithms, and of course there is a huge knowledge in this domain, right? Think of, for example, of algorithm like A-star, alpha, beta pruning, the automated reasoning, the foundation of logic. It's a wonderful domain, right? And then there is machine learning, right? And it is completely different. It looks like you teach two different courses, right? For years, I was lecturing in artificial intelligence and machine learning. I had the impression to teach two different courses. The major difference emerged in the last few years because of the major role of data, right? So what is the difference here? In the pink cluster, Here, the goal is data, right? So essentially, the larger collection you have, the stronger you are, right? But if you go toward this direction, it's not so strange that top-level technology will be in companies, right? Because if you want to compete with the stronger, well, I think it's hard for scientists, right? There is a very good organization in this company for, collection of data, computing technology. So this is, the big difference. And I just wonder whether we can also think of a sort of collectionless machine learning. So, these topics, all of them are collectionless, don't need data collection, right? Problem solving, suppose you want to solve the Rubik cube, right? They are very nice algorithms that don't need data collection. They are smart algorithms for solving, the puzzle, okay? So no data collection. They are collectionless. What about machine learning? Couldn't it be the case that also machine learning is collectionless? And because, we are just taking for granted that you need collection. Do we? Do we really need collection for learning? This is what I'm asking today, right? So, of course, this opens a sort of challenge, right? Can we learn without data collection? Can we design a machine just like this one, right? This is the typical picture, once again, that you see in popular Norville Russell textbook. Can you learn from the environment and from other agent interaction? So, my understanding is that you should start thinking about learning as environmental and agent interactions, right? So you may have environmental interaction and agent interaction, right? In machine learning, look at this keyword, right? These are quite natural keywords that you find in machine learning, right? So unsupervised learning, self-supervised learning, and of course you don't need humans for distributing this kind of collection, right? You may have plenty of data for unsupervised learning and also for self-supervised learning. Here you need interactions, right? So at the end of the day, instead of staying simply with the keywords of machine learning, just use the ordinary framework that you have in cognitive science, right? So you have environmental and agent interactions, just like us. We can communicate, right? And we have information from the environment, the light here, for example, right? The visual information that we have. Okay, so it looks like, maybe we don't need this distinction, right? We don't really need to have the framework of machine learning with this appropriate distinction of the protocols. What is important are environmental and agent interactions, right? So the distinction disappear also concerning, let's say, test and learning phase. Test and learning phase is a distinction which is related to the statistical view of machine learning, right? But of course, in nature, you don't have such a distinction, right? It's a bit embarrassing, right? You see, chicken, or you see cat, dogs, humans. And of course, there is not a time in which they learn and a time in which you experiment their behavior, right? It's a bit tricky, what we have been doing, right? And it could be interesting, right, to take the layman and ask, and talk about how machine learning it is working, right? It could be a bit odd, right? You could say, what? So for learning, you need all this collection of data, but, a chicken learn without such a data collection, right? They learn from interactions, just like humans. We learn from interactions. And then there is plenty of information available during their life. And please consider that the life takes a lot of time, right? The life has the temporal dimension, right? And one of the obvious consequences is that time, has this pleasure, this interesting property of being a number which is not bounded, right? So you can think of the infinite dimension of time. So what could be the learning in the environment? For example, the typical prediction of what happened next. I suppose you consider a music signal and you want to predict what comes next, right? Just like in large language models, so you want to make a prediction of a missing part. And then, what are the interactions? The interactions are, of course, the interactions with the environment. So you have a temporal dimension, right? And so that's the big difference, right? Suppose that instead of dealing with collections, you simply need with streams, with data, right? Just like, in nature. For example, if you think of particles and you think of the temporal dimension, they move according to laws, and there is time here, right? So it could be the case that, the teacher is somehow describing a musical piece, and later on the teacher is playing, right? And so the student has to understand the connection, right? Because at the very beginning, the teacher was explaining what was going to play, right? And here there is the performance of the of the teacher, and later on you ask the student to exhibit himself, right? And so this is a completely different way of thinking. You don't need to accumulate data, right? What regularly happens is that the student, begin playing guitar without, necessarily having, in his her brain a collection. We don't actually have the recording of our experience in the sense that we use in computers, right? After this talk, all people in this room will, exit the room with a very, elegant, abstract interpretation of this talk. You don't need to, of course, remember all the words I was saying. You don't need to record it, to have a precise description of my shirt. You don't need to, many things, right? You will have a very elegant, compact interpretation of this talk, which is useful for you, right? And so at the end, it is collectionless. Can we do the same with machines? Of course, look at one remarkable difference, right? For example, what is quite obvious is that in the typical interaction that there is between humans, there is this crucial role of the teacher, right? And of course, there is a dialogue, and there are levels of development, right? So one question that naturally comes from a truly scientific viewpoint is, why is it the case that, before being exposed to the Euler-Lagrange equation, or let's say to the Euclid theorem of the great common divisor, you have to go to the primary school? Of course, everybody has quite an obvious answer to this trivial question. But it's not what we do with machine learning, right? Which is a bit strange, right? We put all together, right? And of course, in that case, if you are stronger, maybe it's better, but it's a bit embarrassing, right, to learn in this way. So, very interesting. There are so many clever things that we humans do that are not actually implemented in our machine learning frameworks. I coined this paradox of the nerd teenager, which more or less is the following. Suppose just at the door here, there is a nerd teenager, right, who was aware of this talk on artificial intelligence. At the very beginning, the nerd teenager say, oh, this is going to be a sexy talk. And maybe after, a few comments of mine, he decided, you know, to go somewhere else, especially if the topic is from, you know, let's say, suppose I start to give details on backpropagation and on its computational efficiency with the questions which cannot be understood, right? He's so smart that he knows that it's much better for him, you know, to use the time in a different way. We don't have such a clever mechanism nowadays in machine learning. So my interest in the last few years was in, you know, doing my best to think of a theory. I call this theory cognidynamics. It's a sort of thermodynamics of neural networks for, you know, creating again a new theory on how neural propagation take place. It's something where essentially, instead of going directly to the algorithm, I think it's better if you start from laws of nature and you consider the primary role of time. Years ago, there was a very nice paper by Francis Crick. You know, Francis Crick was the you know, Nobel Prize in DNA, and Francis Crick was involved in the parallel distributed research processing with people like Geoffrey Hinton, Ramelhart, McClelland during the 80s. And he wrote a very influential, very interesting paper on the biological plausibility of neural networks. He came up with a conclusion that there is no biological plausibility at all. And many scientists later on, including people like Geoffrey Hinton, you know, made comments, tried also recently to provide motivation for, you know, also the plausibility of backprop. But at the end of the day, I strongly support what Professor Crick was saying, and I want to give you a picture, you know, on how far we are from biological plausibility with the kind of neural propagation that we have. I'm confident everybody is familiar with one of the most popular algorithms in machine learning, the backprop algorithm, right? So essentially you are given a multi-layer network. Suppose you have the teacher here, could be self-supervised if you like. Well, if you have to process a stream, as we normally have to do in a collectionless framework, you have to process, you know, one frame after the other. And interestingly, let me, before showing this, look at what happened in backprop, right? You have to perform the forward step and then the backward step for the update of all the parameters, right? It is nice because this algorithm is optimal in terms of computational resources. It can be shown that you know, it's much smarter than the ordinary numerical algorithm, but unfortunately you have to keep fixed the input here, right? And suppose that you have to make all this computation, right, as normally happen in streams. It means that in order to propagate the error, the information here has to keep fixed until the forward and the backward step terminates, right? So what if you do something different, right? Suppose that, you know, you try to propagate a sort of forward wave, right? Something like this. You see the neurons, there is a blue part, and the blue part is filled when there is the forward process. And then you have that the red part fills when you have the backward process, right? And of course, after a while, you can see units where both the forward and the backward information is available. And this is the time in which you can compute, you can use backprop for computing directly the gradient. You don't have to wait for the forward and backward propagation. This is what Francis Crick was criticizing, right? So if you actually incorporate time, there is this possibility, right? So this is, frankly speaking, you know, what I like most, and it's nice. You can pose questions like, you know, learning take place without accumulation of collections in nature. Is it possible to devise collectionless machines to gain intelligence skills like in nature? I think, you know, this is a good question to pose. And I think it is possible. We did research in the last few years where I'll give you just a very brief picture, but the idea is pretty simple. In traditional machine learning, under the umbrella of statistics, right? What you do, at least in a very general way, is what you see here, right? Any classical textbook or statistical machine learning is centered around this notion of loss, function, and functional risk, right? So you are given a joint probability distribution between the input and the output, and then this joint probability distribution is used to weight properly a loss function, right? And at the end, you have to optimize the functional risk, and all is around, this framework. But suppose that instead of using this integral over, x and y, which, as you know, is done by using from the algorithmic point of view, using an empirical risk, suppose you replace by the integral over time, which means that the averaging of the error are just over time, right? So you don't have the distribution. Since the very beginning of your life, nobody has this, this opportunity of having his life, the collection, the pieces of the bit of life are not available for us, right? What we do is likely something like this, right? We accumulate the error over time. And so that for what I understand, this is likely the closest scientific description, right? In theoretical physics, this is pretty common, right? So it is nice to see that laws in theoretical physics emerge, for example, because of the minimization of functionals, like in analytic mechanics. If you take the stationary point of the action, which is the difference between the kinetic energy and the potential energy, what is interesting is that the outcome of this optimization problem, which at the end is translated into the Euler-Lagrange equations. These are the Newtonian laws of motion, right? And at the end of the day, in physics, what we do is that we do our best to discover regularities, which is more or less what we have to do with, information, right? We have this information and we have to look for regularity over time. That's why I think there is this strong connection. So we started to use the framework of theoretical physics because it's a mature framework with a lot of things which can be reused. So you have the velocity, right? The notion of velocity is the velocity of the weights, how they are changing over time, right? Then you have the Lagrangian, then you have the Hamiltonian, and then you have the Hamiltonian equations. And so it's so nice because you can quickly see the possibility of taking neural networks. Please consider recurrent neural networks. You don't need to have, of course, the typical structure that you have, for example, in deep learning, right? In deep learning, don't forget that most of deep learning is associated with the assumption that there is a direction of the flux of information, right? You go from the input to the output in a sort of forward step without, a dynamical process. So it's possible on the opposite to generalize what you have seen in the previous picture, where I was showing you the forward and the backward wave. So the theory can, at the end, explain how algorithms that were invoked by, for example, by considering the biological plausibility. The comment I told you came from Professor Crick. Now there is not this limit, right? Because there is a sort of spatio-temporal locality, and is something which is really close to what you see in other natural sciences. Now, in the last few minutes of my talk, instead of focusing on this part, so on these ideas of nature-inspired learning, of course, I will be delighted if you have if you are interested in this part, which is actually the part on which I'm spending more time, maybe the part at least that I like most. But I think I have the duty and the pleasure to tell you something different now, right? And the difference is something that emerged during the last, the discussion we had in the last, few months, especially in the lab, right? One of the difficulties in following a different direction, so this direction of collectionless AI, is that you are not in the mainstream, right? So, of course you can do research, but, maybe you are also good, but if you are not in the mainstream, especially nowadays, it's not good for you, right? I think this is a very serious problem in science in general, because there is too much emphasis on, the fact that you belong to the mainstream. But it is something concrete, and we have to consider. But there is also another reason why we started to consider what you see here. So a sort of technological attempt to, introduce another view of machine learning. What we call, a sort of universe, a universe where you have humans and machines. We actually need to change also the concrete framework, because nowadays, everything is around data collection. You have also to give the opportunity to scientists to, experiment what I was telling you about. At the moment, our experiments are just in our labs, with, just a few experiments where, we can develop ideas just like others on, this temporal view. But it is important, I think, to involve other people, at least people who like this approach. And so look at, what I say here, right? So in our understanding, goal in this view is not data collection, but interactions. So is it possible from a technological point of view to construct something which enable to handle the interaction? Well, frankly speaking, even if I'm professor of computer science and I taught during my career many courses in computer science, I cannot claim to be really an expert in this kind of technology. And as I told you at the very beginning of my talk, there are a number of people who have been contributing towards the conception of what we call universe, right? But the idea is pretty simple, and I did my best to, at least define the foundation, the basic principles. So instead of having, all the power, the computing power and all the data in one single point, or two or three, suppose that you consider the billions of CPU available worldwide, right? And you think, just like in a fiction movie, right? You start thinking of onboard intelligence, just like in nature, right? So it's a completely different picture, right? Because there's so many CPU worldwide. It could be the case that for the year to come, some of them, maybe not all of them, but some of them could become intelligent machines, right? In the sense I was telling you about, collectionless intelligent machines, not machines which are driven by, an enterprise which collect all data and a specific technology, right? But something which is spread worldwide, okay? So how can this be possible, right? The principle behind this notion of universe is something that I found it is very well described by this popular picture for who, all of you who have seen some movie on, or maybe are aware of the early telephone technology, right? There was this popular sentence, "Hold on, I'll put you through," right? During the telephone call at the very beginning. Essentially, they were collectionless. What about doing the same? So, to construct a technology where everything is collectionless. You don't have somebody, the dragon, Mr. Dragon, who collect all the information. You simply, you'll put them through, right? And look at this picture, right? I think it's somehow giving you in touch with what happened nowadays in large language models, right? So you may have two agents, right? And there could be, you can think of an interaction between the agents, the agent and the environment. And well, nowadays, we have seen remarkable advances in large language models exactly because of the environmental interaction and the agent interaction. So, for example, in GPT, where can you see the environmental interaction? Of course, in pre-training. It has been of great importance, of enormous importance, the self-supervised step that you have in large language models. Because in large language models, you have this opportunity from big companies, they can collect a lot of information and they learn to make prediction of what happened next, or maybe to predict missing parts, right? They try to develop learning from the environment, right? And then, in order to respond to query in a pertinent way, you need the interaction also with agents, with humans, for example, right? Or with other educated agents, right? And so we already have in companies, right? Nowadays, for large language technology, this distinction, right? But of course, we could pose the following question, right? First of all, why should we strictly separate pre-training from agent interaction, right? In life, it's much, much richer. And the question is whether, this can be done even without data collection, right? So look at how agents looks like in this picture. You may have agents, right? And please consider an agent could be a human also in principle, right? But suppose they are artificial agent. What you have is each agent in principle can expose worldwide an environment. Suppose a music environment, right? I'm singing something, I'm playing something, and I want to make this performance available worldwide at this time, right? It is not going to be let's say, a collection of data, a collection. It is not going to populate a data collection. This is something that you instantaneously are making, right? So you are singing now, okay? And so what you are doing is that in principle you can make this information available. There could be a meeting room also, somewhere, right? And also in the meeting room you have information available, okay? And of course also interactions available. And the agents, of course, are in different positions worldwide. There is a distributed computation, right? So that's the picture. You have humans and machines, right, which communicate, right? And what is important is that the communication is collectionless, right? You see, no recording here. And the agent, under the control of humans, who will decide who are your friend, who want to speak to, right? And so essentially you could say, how can you measure, how can you see the progress, right, of this technology? Well, instead of having the benchmark, and the benchmark nowadays in artificial intelligence come from statistics, right? And that's why, statisticians, can give fundamental contribution on machine learning, at least so far, right? Because we are in a sort of statistical framework, right? This is a bit different. In principle, you may have an agent, yet another agent, who is the teacher. And the teacher, for example, at this time, is checking the behavior of 3 agents, just like in ordinary interactions. And as you know, it is going to be much more sophisticated than just simply exposing the accuracy on a given training set. Your cognitive abilities, your intelligence, the reason why you are appropriate for some task is not necessarily associated with a single index or 2 or 3 indices or performances that we are nowadays measuring. And it's also interesting to notice that the explosion of OpenAI was not based on mostly on the fact that they were winning on traditional benchmark. It was based on the diffusion worldwide. So, of course, when you have this framework, you can think of the exploring of a sort of, let's say, emergent behavior, because you have so many agents which interact and their emergent behavior. But you have to consider that you have some novelties which come. You need a sort of conscious model, because you need also to decide when the time comes for talking, for example, right? So maybe you can solve a task, but before exposing your response, right? So apologize. So before exposing your response, you see, you have to enable the output, right? This is typical in human interaction, right? When you know very well that our own decisions are not just based on our expertise, right? They are context framework in which the time comes for all of us in which you have to talk, right? It is not necessarily the case that you talk continuously, right? So this is another important part. And let me show you why we also, very briefly, we are creating a technological framework which could be much more interesting than what you see from the typical emergent social behavior, which is still interesting, right? But you can do something much clever, right? Which is quite obvious. You can inject social plan, and social plan are simply, what you regularly see in our relationship. Think of the typical relationship student and teacher, right? So you can think of a social developmental plan where you start from state x0, right? Then a teacher, which is in this state, for example, announces a course, the student is enrolled in the course, and later on the student can decide to take the course. So you are in a sort of committed state, then somebody will tell you that the course starts, and then you have the typical cycles, right? Because there is an assessment, and you may fail the exam, and maybe you need to learn again. Well, I don't have time to go into the detail, but I'm confident you understand that if you think of events and states which characterize the developmental plan, you can formalize the interaction that you have, for example, in traditional courses, and you expose the agent to a completely different kind of information with respect to what we have nowadays, right? So we have events, right? And these events are characterizing everything. So just before closing, the talk, I want to tell you that in principle, suppose you are in your lab an agent, so that's the main body of your agent, okay? You can include a few methods for communication. So at the end of the day, this is still your agent in the lab, and this can start, this can, you can activate a connection with other agents, right? So this one can communicate with another agent, okay? And later on, the agent can also become part of, for example, a classroom where you have a learning layer. Remember the previous discussion on the developmental plan, and this is a framework in which at the very beginning it is good. This technological platform is going to be simply a showcase, right? So you have your technology and you can just publish what you have in the lab, because Universe will allow you to make your technology available. Others can pose questions, so can interact. But the second step is that you can start to benefit from social interaction. And here is the learning layer. And finally, what I like most on the long run is that you can start thinking of new machine learning where you don't really need to start already from something which is available, but you really want to produce technology which learn only from in the temporal framework. So just to tell you what is in the lab at the moment we have an internal technology where, for example, we have been using this technology for social interactions. We have done some experience in computer vision. You see, this is what the software produces for these developmental plans. But I want to close the talk mentioning that, of course, there are many other related approaches, but frankly speaking, there is a remarkable difference, right? There are related approaches. Here is a list, right, of emergent technological solutions. I don't know whether you are aware of some of these initiatives, but the big difference is that most of these initiatives come from the old idea, what I call the old idea of machine learning, right? So, for example, they are most on federated learning, which of course is very useful, right? For example, in medicine. But still, there is not the principle of collectionless, right? So the kind of technology that we offer is something where you start with, concerning privacy issue, there is a sort of privacy by design, right? Whereas this is not a typical framework in which this technology emerges. So just to close, I think, in nature, it is quite common to see the beauty that arises under the relentless effect of time, right? And I'm confident something similar can happen in cognition, right? In artificial cognition, in AI. And there is something that I think is worth mentioning. The amount of information of large collections cannot be compared with that produced worldwide under the relentless effect of time, right? So if you look in perspective, this message is for telling you, especially young people, right, that of course there could be, the effort for still organizing big collections, right? But there is something on the corner that at the moment is completely, dismissed in theoretical analysis and in science, that I think it deserves our attention, right? Because if you think in terms of amount of information, which of course is extremely useful for learning, right? Any statistical principle is telling you that, of course, the amount of information is important, does matter, right? But what is important to notice is that, if sooner or later the direction of collectionless AI somewhere in the world will take place, at that time, please consider that in addition to the information that can be produced from the web and from artificial intelligence and from agents, this information can be produced directly from the environment and from humans, right? And so that's why also from the quality of intelligence on the long run, that could be an interesting direction. So a few conclusions. In the conclusion, I just want to say that for all of you who are interested in, for example, joining the challenge because you have something in the lab and you want to expose what you have, this is you are welcome. If you are interested in joining this challenge, of course, just drop an email at this address here. And there will be a public announcement. It's the first time I give a talk on this topic. There will be an official announcement in the next less than a couple of months. We plan on June the 15th to have the technology available. At the moment, as I told you, is in the lab. So we have these, the agents are simply agents which are in the Python, in the PyTorch software that I showed you. And beginning from July the 15th, we will invite colleagues to try and to see what could be the direction. Thank you so much for your kind attention.